So, welcome back again, and as per my promise, I will talk to you about simple pendulum. There are pendulums of various kinds. Some of them are simple. The one we are going to discuss here is simple pendulum, and there are compound pendulums, and there are anything which is fixed to a ceiling and then it is disturbed and then it starts oscillating. So there are periodic oscillations, not necessarily simple harmonic motion. And if the air over there is effective, then after some time damping starts and the oscillation come to a stand still. So it happens. But right now we are taking the ideal situation where the pendulum will not stop once it has been started. The pendulum is a ball of mass m, which is supported by a rigid support. Okay. And once it is disturbed by an angle theta naught to an extreme position, this time it is to the right hand side that we have taken, and then this position is called the mean position. This is the extreme position at theta naught, and then it is released, then the pendulum starts oscillating. Before I go for other things, I'll tell you one thing. My string over here is massless. Okay. We consider it to massless, it is not massless. Okay. And this is under that condition we call it an inextensible string. Okay. So many qualifications to it. Thereafter, what happens? Right now you can see that the level of the mass is here, which is some distance above the mean position. Right now it has no kinetic energy because it is going to be released with a velocity which is equal to 0. Right now all energy encompassed over here is potential energy. So when I release it from this position, then the potential energy gets converted into kinetic energy until this comes to this position. When the kinetic energy is maximum, the potential energy is 0. Then again it goes in this direction and is brought back and goes not to and fro but one side to the other side. The motion, of course, is a circular motion. A circular motion in a vertical circle. Okay. So whatever I taught to you about the vertical circle case is true here also. So it is a change of potential energy into kinetic energy and kinetic energy into potential energy. They trade for each other. The word is trade. Trade. What it means? Like we pay money to the trader, he hands us over the goods. Okay, so there is a trade going on. Is haath le, us haath de. Okay, like that. So anyway, now this thing is just a description of the simple pendulum of length L. Remember that. The length is an important factor, so I am emphasizing it. The length is there and there is angle theta naught. Normally this angle must not be more than about 20 degrees or it is better if it is not more than 10 degrees. We will see why. Now let us see. I have just another picture of it. Okay, the massless string, there is still air, and the air is not offering any viscosity, any damping forces. Okay, so this is all consideration, that no damping. This T is for tension. In fact, when we are doing physics, then we are short of symbols. Let's see that this is for tension and this T is for the time period. Okay, you have to understand that. I'm not going to write T and T dash, etc., etc. Okay, so now while it is swinging between the angle theta naught and minus theta naught, okay, let it be, let us consider its position at a point theta, at an angle theta. So theta is a general angle, it's other than this theta naught, which is more than theta, of course. Here I just take it to be a little different from that. Now let's see, what are the forces on the bob of mass m? Our spherical bob. There are two things. One is the tension in the string, and because tension is both ways, so it is because at this point there will be, any point you take over here, there will be tension like this and tension like this, but the effective tension is towards the point of suspension O, and you can see this is the tensional force which exists over here, right? Now there is another force, and though that force is mg due to gravitational pull of the earth, where g is the gravitational field or acceleration due to gravity. Okay, I've told you all these things before. So these two forces are there. Now these two forces, this force mg can be resolved in two parts. One along the length of the string, which is mg cos of theta, and the other is perpendicular to it, which is mg sine of theta. So the radial force actually becomes T minus mg cos of theta, and the tangential force over here becomes mg sine of theta. Of course, let's say, what is the radial acceleration? Radial acceleration is equal to omega square into length L, where omega is d theta over dt, which we also sometimes write as theta dot, which is 2 pi nu is equal to 2 pi over capital T. All these symbols you know from before. And tangential acceleration is, we will see, and I leave it to you to understand what is the tangential acceleration. I apply something over here which you have got plenty more than what I have. I've already spent a lot of it, and you have a big lot of it, so use that. Then let's try to find out as to what is the torque, because there is a rotation. What is the torque about the point of suspension O? And I'm again writing for you. I'm asking you, what is the axis? Then look here. I'll answer that. The axis is like this. You can say out of the board, if this is xy plane, then this is in the z direction, out of the board or into the board. So which we represent out of the board as like this, and into the board like this. So whatever you want to think, it is an axis which is perpendicular to the plane, and the oscillation takes place. Well, the torque about this axis is equal to L, the length over here, and into the perpendicular force that is there, mg sine of theta. So minus L mg sine of theta. Why? Why we write it minus L mg sine of theta? Because this torque is a restoring torque. tending to reduce the angular displacement theta. Okay, angular displacement theta. Okay. Now I can write this torque as equal to I into alpha, where I is the moment of inertia and alpha is the angular acceleration d2 theta over dt2 or theta double dot. Okay, so from here we try to obtain the equation. So I get the value of the torque. Torque is equal to I alpha is equal to minus mg sine of theta into L. Okay, mgl sine of theta. Sorry. So alpha, the angular acceleration becomes equal to minus mgl upon I into sine theta. Now this I is equal to the mass into the distance squared, because they are perpendicular to each other and this direction, and it is equal to ml squared by definition of the moment of inertia. Okay, well, so alpha I can write as equal to minus mgl upon ml squared sine of theta. So m and m cancel out. It's important. That means whatever we are going to, the results are not going to be a function of mass. So I can write alpha is equal to minus g upon L into sine of theta. Now the expansion of sine theta says that sine theta is equal to theta minus theta cube upon factorial 3 plus theta 5 minus plus etc. factorial 5. If the value of theta tends to 0, this value, these are negligibly small, all these terms, and therefore sine theta becomes equal to theta, which you can also understand if you take a small angle, then of course theta becomes equal to, theta is equal to arc upon radius and sine theta is equal to perpendicular upon hypotenuse, and therefore sine theta turns out to be equal to theta itself. And if I want to know as to what is the value of cos theta, if theta is small, then cos square theta is equal to 1 minus sine square theta. From the Pythagoras theorem, it is approximately equal to 1 minus theta square. So cos theta will become equal to under root of this 1 minus theta square, or 1 minus theta square raised to the power of half, which by binomial expansion turns out to be equal to 1 minus theta square upon 2 if theta tends to 0. Anyway, it was just a byproduct. Okay, what is needed is sine theta is equal to theta. So d2 theta upon dt2, which is alpha here, becomes equal to minus g upon L into theta. Now this equation we have to concentrate on, and I can compare this equation with d2x upon dt2 is equal to minus omega square x. So when we compare, then what do we find? That this is the angular acceleration, this is the angular displacement, this is the linear displacement, linear acceleration, this is linear displacement. So omega square will turn out to be equal to g upon L, which gives omega is equal to, as defined, 2 pi nu is equal to 2 pi upon capital T is equal to under root g upon L, which gives the value of T becomes equal to 2 pi under root L upon G. Okay, 2 pi under root L upon G, and then you can find out as to what is the frequency, etc., etc. Now there are two things. One I have written over here, that this time period or this frequency is independent of the mass over here, and as long as theta tends to 0, this is also independent of, not a function of the, is not a function of this amplitude, which is theta naught. Okay, so it doesn't depend upon the amplitude, doesn't depend upon the mass of the pendulum. Okay, so that finishes with the simple pendulum. And now that I have described simple harmonic motion, I have described it in terms of d2x upon dt2 is equal to minus omega square x, and this omega square is equal to k upon m, etc. And then taken you through the different things. You can also talk about the total energy of the system, kinetic energy, the potential energy, the total energy, like has been done for the simple harmonic oscillator. All those things you can do once you know as to how this can be dealt in. It's very simple. We have just taken the angular velocity, the angular acceleration, and the value of I is equal to ml square, and then substitute things, taken sine theta approximately equal to theta, in which case the cos theta becomes equal to 1 minus theta square by 2, etc. And learned that the simple pendulum behaves like a harmonic oscillator in one dimension, going to and fro, back and forth from a position of rest, which we call equilibrium position. If the disturbance is there, then the oscillation is there, and this is true of all kinds of oscillating or vibrating bodies, that they have to have an equilibrium position. There has to be a disturbance, and that disturbance has to be small. Okay, in all cases that disturbance has to be small. So this is how we say. And if there is a damping, what will happen? So that is the case of damped oscillators. Damped oscillators are very interesting. Very interesting. The physics is very interesting. And then there is another thing for which the physics is interesting, and that is forced oscillations. Damped oscillations and forced oscillation, I differ. Okay, I'm not taking up right now. I am going to differ, which means in Hindi, it means hit kabhi. So towards the end of, when I complete the course, then I may take many cases which I have left, and which, if you are interested, and you must be interested, you can go and study these things. One thing I'm going to tell you and share with you, that the simple harmonic motion, the simple harmonic oscillator, and these various kinds of oscillators, the energies, etc., they are very, very, very interesting. Of course, they require little bit of scribbling on your part. Okay, even the students, I have tried, even for the students who don't have a mathematics course along with the physics course, that is, they have instead biology and things like computers and things like physical education, etc. Okay, and maybe after some time there is one course, how to deal with corona. Okay, and the social distancing and this and that and that and that. Well, even for those students, I have tried to make the tedious mathematics. Some of it I have developed myself. Okay, I'm not the originator, but I like that, and that is why I say, because other people don't use it, this method of mine, therefore this is exclusively my method. Use it. But if you are writing an examination, don't write there, because your teacher, the madam is or the sir who is checking your answer sheet may get confused, and once there is a confusion, there is something like this always, and what results is a 0 for you. Okay. So beware of that. When you are writing the examination, don't take my method of differentiation. What is that? If sine theta or cosine theta are differentiated with respect to theta, then their phase enhances by pi by 2 radians, and if it is integral d theta or dt or whatever, then whatever I had, the phase again enhances by minus pi by 2 radians. I don't say it is reduced, I'll say it increases by minus pi by 2 radians. So thank you very much for being with me, and I've enjoyed your company. Please enjoy the output of these discussions. Thank you very much.